Briefly, a quick introduction of what inelastic collisions are. In physics, an inelastic collision occurs when the maximum amount of kinetic energy of a colliding object/system is lost. The colliding particles stick together in a perfectly inelastic collision. In such a case, kinetic energy loss is used in bonding the two bodies together. Now let's start off with the first problem, the developing question. A 4 kilogram meatball is moving with a speed of 6 meters per second directly towards a 2 kilogram meatball which is at rest. The two meatballs collide and stick together. What is their velocity immediately after the inelastic collision? So now, first, we need to draw our collision diagram that breaks down the problem's collision a little easier, which is this. So we draw the first meatball, draw the second one, we draw what their masses are and their velocities. Next, we use our momentum formula, which is momentum initial is equal to momentum final. We expand it into mass multiplied by velocity for each one of the objects. And then the momentum of the first ball plus the momentum of the second ball equals the total momentum. And then we just rearrange to solve for our total velocity. And finally, when we plug it all into our calculator, we get a value of 4 meters per second. Now, the reason that this is a developing level question is because it introduces the basic ways of utilizing momentum formulas and how to identify what is happening during the collision. Now for our second problem, the understanding question. A 1,000 kilogram car is moving eastwards at 20 meters per second. It collides inelastically with a 1,500 kilogram van traveling northwards at 30 meters per second. What is the velocity of the two vehicles immediately after the collision? So first we need to draw out our collision diagram. And we know that this is a two-dimensional momentum problem because the question has added direction of north and east. The primary step is to break our momentum into components of x and y. Next, we are going to use our momentum formula. Momentum initial is equal to momentum final in the x direction. We expand it into mass multiplied by velocity and cancel out the velocity of the second vehicle because it does not have any x component. Then we rearrange for our total velocity in the x direction, and we get 8 meters per second. Now we repeat those steps for the y direction. We cancel out the first car because it does not have any velocity in the y direction. We rearrange for velocity total in the y, and we get 18 meters per second. Now we can take the velocities in the x and y direction and create a triangle solving for the vector velocity using the Pythagorean theorem. We get a squared plus b squared equals c squared, and then we get at the end we get 19.7 meters per second. Now because it is a vector problem, we also need to find the direction. So we use basic trig and we find out that theta is equal to 66 degrees. Therefore, the final answer of velocity with this collision is 19.7 meters per second east, 66 degrees north. Now, the reason this question is in the understanding section is because it uses our knowledge of components of the x and y, and it requires a little more understanding of how directionality works in relation to collisions of east and north. Now time for question 3, the mastery question, the hardest one of them all. The question is, a block of mass 7.3 kilograms is attached to a 3.8 meter string hanging from the ceiling. A bullet of mass 13.5 grams is fired horizontally into the bottom of the block and stops in the block. The maximum angle the block and the bullet combination reach is 18 degrees. What was the initial velocity of the bullet? First, we need to identify that this is a ballistic pendulum problem, which means it involves momentum but requires a little bit of a different approach. We need to draw out the ballistic diagram to see the motion of the block and the bullet. This is what a ballistic diagram looks like. So first we have to draw out the different stages of the maximum angle it reaches with the rope length, the part where the bullet's actually inside the block, and then before, where the bullet's just been fired, we don't know its velocity, and the block is just hanging by the string. So our first step is we're going to need to calculate what the height at which the block is off the ground, delta H. We do so by using trig and the rope length to find the y component of the rope, H. Then we subtract the rope length by our calculator length to get delta H. Done so here. So we get a delta H of 0.18 meters off the ground. Next, we use our energy formulas of kinetic energy is equal to potential energy because the energy of the moving system will transfer into potential when it reaches its maximum height. Next, we need to use our momentum formula. Now, before we used our momentum formula, we just solved for the velocity total of the block as soon as the bullet is inside of the block. So the total velocity, once the bullet transfers all of its energy towards, we know what that speed is. So we take P initial equals P final, and we separate it into into mass times velocity, and we know it's only the initial velocity is only the bullet because the block is at rest, and the final velocity will be all of them together. We plug in our known values that we've just calculated for, isolate for the velocity initial of the bullet, and we get an answer of 1,034.7 meters per second, which is just rounded to 1,035 meters per second. Now, this question is in the mastery section because it introduces ballistic pendulums and the conversion of energy and how it relates to momentum. It shows the link between momentum and other physical concepts, like trigonometry and energy. Now, you're probably wondering what are some real-life applications of inelastic collisions. Where do we see these in our day-to-day lives? Now, a couple examples of that is a car crash. So in that second problem we did, the 2D dimensional inelastic collision one, in a car crash, if two cars are going at a certain speed and hit each other and then stick together and then slide off in a certain direction, that is an inelastic collision. Another example would be a bat hitting a baseball. Now, when hitting a baseball, the ball compresses onto the bat until it has enough forward momentum to fly off. So you transfer the momentum of the swing of the bat into the ball, which launches the ball away. The final example would be being shot. So a bullet embedding into the torso. So not as exaggerated as the movies put it, but when a bullet hits you, you move back a little bit because of the bullet's momentum transferring to you. That is all. Thank you for listening. Hope you enjoyed.